All right, we're going to use a couple of different ways to think about limits. We did limits last time, and if you'll recall the screen, we found out and thought about limits in terms of a graph, so that if we had a graph and we were looking for the graph of ln x, which looks roughly like this, and we looked at the limit as x goes to infinity, we found out that it was infinity. If x is approaching 0, the limit does not exist because it does not exist on the left-hand side of 0. And then the limit as x approaches 0 from the right-hand side would be negative infinity because the graph is approaching as it is approaching the y-axis, it is plummeting. And then as x approaches 0 from the left, it doesn't exist again because it's not on that side of the graph. So what we want to think about in terms of this graph is, what does it look like if we were to sketch it from what we remember? And what I mean by that is that -6, what does it do to the graph? So if you think about that -6 is in the location where it moves the graph either left or right. And because it's negative, it actually moves the graph to the right-hand side. So we're going to take a look, and our axis, y-axis, is going to move over here to x equals, well, let me fix that. Going to move to x equals 6, and then otherwise our graph is going to remain unchanged. So it's going to look like this after that new asymptote. So if we're approaching 6 from the right-hand side, it means that we're tracing along our graph going this direction, because we're going from the right-hand side, and again that means that we are then plummeting. So our limit in this particular case is then infinity, and it's negative because we're going downward forever. All right, so this kind of leads us into the next sort of natural topic after limits that you encounter in calculus with any function you're dealing with, and that's the concept of derivatives. Now, using the information we have done before and thought about how we defined what the natural log was, if f of x is the natural log of x, then its derivative is actually 1 over x. And using that idea combined with one of the techniques you've learned before called u substitution, we're able to find the derivatives in the next few slides. So this first one right here, this is a function that's a natural log, and it actually has x minus 1 on the inside. So this has a chain rule involved, although you'll see very quickly it's not a very interesting chain rule. So the outside derivative is the 1 over part, and it's 1 over the inside rewritten. So we've got x minus 1 in the denominator. And then very technically we would multiply by the derivative of x minus 1. The derivative of x is 1, and the derivative of 1 is 0, so we actually end up with the derivative of 1 here. So this is just 1 over x minus 1. This one's a little bit more interesting, and at first glance you might think, oh my goodness, I've got a quotient rule here. And I've also got a chain rule here, and this looks like it's going to be really messy. In reality, you don't. Not if you simplify this first. So the thing you want to recognize is this is a log, and logs have wonderful properties. In particular, this property right here will be useful to us. We can separate the quotient here with subtraction of logs. So this will be the natural log of x minus the natural log of x squared plus 1. And the good news as we're working with that one is that I then do not have a very complicated chain rule that involves a quotient rule. In fact, I don't have a quotient at all. So I haven't done any calculus yet, I've just used properties of logs. Now I'm ready to do the derivative of the calculus part. So I have natural log of x, and that one is just plain out my flat old rule, 1 over x. And then I have to subtract, and I have the natural log, so I've got 1 over. I rewrite the inside, x squared plus 1. But then I need the derivative of the inside, which would be 2x. Now, I can certainly take one real quick step, and I can rewrite this so that I have the 2x on the top of this x squared plus 1. But I also need to combine this back into a single fraction, and the reason that that is where I actually need to head is because the original problem was given as one single fraction. So my answer should also be in that form. So if I do that and I get a common denominator, the denominator would just be the two denominators multiplied together. So I'm going to have x squared plus 1, and that's what I get when I multiply the number 1 by that. And then I'm going to have minus 2x, and that needs to be multiplied by the first denominator, which is another x. And then my new denominator will be x times x squared plus 1, which I want to leave in this form because it may be more helpful to see that later. Now, obviously, this right here is actually 2x squared, and it's negative. So I can combine that 2x squared with the original x squared at the beginning, and I end up with the solution negative x squared plus 1 over x times x squared plus 1. And that won't have any canceling features going on because in the numerator I have negative x squared, and then in the denominator I have positive x squared, but the plus 1s are identical, so I don't have anything I can factor out a negative or anything to reduce that, and this is my final answer. Let's take a look at this one, which is a little bit more complicated. It's the same sort of flavor to it in the sense that I've got the natural log of a problem, of course, but the part that makes this interesting is partly that square root and the fact that, unlike the problem before, I can't split this up in any way because I can only split them up when I have products or quotients inside of my logarithms. So I actually have to deal with this one kind of as it is. And as I'm taking this derivative, of course, the first part becomes 1 over. It's 1 over the entire inside function, which is x plus the square root of 4 plus x squared. And then I get to take the derivative of x plus the square root of 4x squared. Now, one thing that might be helpful to remember is that I can rewrite this expression as 4 plus x squared. Oh, let me get that plus back in there. Let's try this. 4 plus x squared to the 1/2 power instead of writing it as a power of, or as a square root. So I need the derivative of this. So the first part I'll do, that one's easy. The derivative of x is 1. Now the derivative of 4 plus x squared to the 1/2, I'll bring my 1/2 down. I will rewrite the 4 plus x squared, which then has a power of negative 1/2. And I have to take the derivative of 4 plus x squared, which is 2x. And all of that is inside the parenthesis with that 1 plus from the beginning. And that might look really ugly. In fact, it kind of does right now. But the cool thing is the simplification is going to be just oh so wonderful. So just bear with me while we take a look at that. All right, so here's what we have so far. I have a really nice feature going on here that this 2 and this 2 are going to cancel because one of them is multiplied as 1/2, the other one is multiplied as 2. And those are multiplicative reciprocals. And then I have 1 plus this denominator, or this 4 plus x squared to the negative 1/2. It can actually be written in the denominator. Now I've got an x in the numerator from the 2x there at the end. And then in the denominator I have square root of 4 plus x squared. All right, so we're almost to the wonderful simplification I promised you earlier. Let's rewrite this first fraction. And if I get common denominators on the second fraction here, I end up with square root of 4 plus x squared plus the x all over square root of 4 plus x squared. And if you'll notice, these are perfect matches, which means they reduce. So the final answer that I am left with is 1 over the square root of 4 plus x squared. You're welcome to leave it that way, or if the square roots in the denominator are bothersome to you, having taken trig, you can rewrite that by rationalizing, so to speak, that I don't have a square root in the denominator. And I end up with, let's see here, the same value over 4 plus x squared then. And then this problem is taken care of. All right, so this is sort of a variance, a little bit of a difference, and you'll see when we get into section 5.2 kind of why I'm bringing it up now. But you'll also see while we're working in this section today an application of when this is useful. So if you end up having a function that is the natural log of the absolute value of x as opposed to just the natural log of x, it doesn't actually change anything in the derivative form. So in other words, the derivative is still 1 over x. It doesn't have any absolute values in it or anything like that. And your book does a good job of showing why that's the case, and I encourage you to take a look if you're interested in seeing that. But for practical purposes of what we're going to do here, I just want you to know that fact. And if you take a look at problem D, we're going to use that fact. So for problem D, what we have is we have to take this derivative. I have the natural log, so just like on all my others, natural log becomes 1 over. And it's 1 over the entire inside except that I don't need the absolute value, so this is 1 over sine x. And then I have to multiply this by the derivative of sine, which we've talked about already as well, is cosine of x, and you should remember from a Calculus 1 course. If I simplify, this gives me cosine x over sine x. And from trigonometry and quotient identities, this very quickly turns into another identity called the cotangent of x. And then we're finished with that one. Now note at the bottom it says the sine of x must be an absolute value and asks you why. This isn't a question that your book is asking you, but it's one where I want you to sort of ponder as you're looking at this and thinking, why did they put the absolute value in there? Was it just so that I could have something to use that rule on? And hopefully you're thinking, well, surely there's more to it than that. And there is. If you think about it, one of the features of that natural log graph was that it only could have inputs that were positive. And if you'll remember, the sine of x graph has actually outputs or range values that go from -1 to +1. That is to say, a sine value could be negative. And if it were negative, I can't take its natural log. So these absolute values, in essence, remove all the negatives from being inside of the log, which doesn't eliminate all the problems, because certainly sine x can also still be 0, and that's not in the domain here. But it at least eliminates the majority of the problems by taking care of those negatives. All right, so take a look at example 7. Example 7 does something that you should remember from Calculus 1. It asks you to find an equation of a tangent line. And if you'll remember, tangent line is sort of code for to find the derivative. So whenever you see find a tangent line, the first thing you're going to find is the derivative. And the relationship is that the derivative, when it's evaluated at the point, in our case this is the point 1, 3, will be the slope of my tangent line. All right, so if we take this and we find the derivative, so the derivative of this is a real clean one. It will become 6x minus 1 over x, which is nice. And then the slope that I'm looking for here will be found by taking that derivative and plugging in the x value in question, which is x equal to 1. So I have 6 times 1 minus 1 over 1, which you can see very quickly is 5. So I have a slope of 5, and I have a point of 1, 3. And hopefully, again, from your algebra courses, you remember the slope-intercept form of a line, which is y minus y1 equals m times x minus x1. This is certainly not the only way to do it, but it's a very clean way of doing it. So I would have y minus the y value 3 equals m, which is 5, times x minus the x value, which is 1. And if you do a little algebra to simplify this, you will very quickly find that y equals 5x minus 2. Using that same information, you can take a calculator to graph the equation in the tangent line. If you do that, you get an image that looks something anyway like this. So you have, oh, let's try again. You have the axis. You have a curve that looks something akin to this as your original curve. And you have the point right here, we'll say roughly right here anyway, which is at 1, 5. Definitely, yes, I realize I have not drawn this at all to scale. And you've got a line, and your line looks something like, let's try one more time. Your line looks something like this. And so a tangent line, if you'll remember from Calculus 1, means that it just touches the graph and sort of bounces off most of the time. That's the description of visual imagery when you have a tangent line. Now the Deriv feature, Deriv is under the Math button in your calculator. And if you select Math 8, which is Deriv, the notation that you want to use is Deriv of y1, and you can find y1 by pressing vars, selecting the y-vars function, and then pressing on function, and then choosing y1. So if you've put this into y1 in your calculator, back when you did part B, that's the y1 you want, the original curve. You put in x next. After the comma, you put in x, and that tells the calculator that you want the x as the variable. And then we're going to evaluate this at the number 1, and all this should be done in the main screen of your calculator. What will happen on this particular one when you do this is you'll end up getting the value 5. That is to say, you'll end up getting the slope for your line, so you can confirm the solution you got over here when you evaluated the slope at the point 1 after finding the derivative by hand. So that's just a quick, easy way to verify that you're getting the right slope for this tangent line, and then there's just a little bit of algebra after that. We have 2 more problems left, and they are interesting problems because they involve some kinds of differentiation that are a little bit challenging. The first one is the equation ln xy plus 5x equals 30, and I'm told I'm supposed to use implicit differentiation. And the reason it needs to be implicit differentiation has to do with the fact that it says natural log of x, y. Now, you can either handle this as natural log xy as though the x and the y are multiplied, and I've got a product rule. Or, if you prefer, you could change this into the natural log of x plus the natural log of y. Now, when we did this in class together, that's actually not how we did it. But just for curiosity's sake, let's take a look and try that now. So I can write this as natural log of x plus the natural log of y plus 5x equals 30. And we're going to take a derivative. So the derivative of ln of x is 1 over x. The derivative of ln of y is 1 over y, but then it's times dy dx, because that's the derivative of y. There's actually a chain rule there, although it doesn't sort of, call out to you as though it's a chain rule. It is one. Derivative of 5x is 5, and then the derivative of 30 is 0. So I'm going to be moving everything onto the right-hand side that's not associated or connected with multiplication to that dy dx. So I'm going to subtract my 5, and I'm going to subtract my 1 over x. So I end up with 1 over y dy dx equals negative 5 minus 1 over x. The last thing I need to do is I need to multiply the y to the other side. So this is dy dx, and I have negative 5 minus 1 over x, and I need a common denominator here as well. So let me go ahead and get this at the same time. So this is negative 5x minus 1, or you could write negative 1 minus 5x, over x, and it's supposed to be multiplied then by y. So I end up with dy dx equals negative 5xy minus y over x. That's implicit differentiation. It's okay that I still have a y attached to this problem on the right-hand side, that it's not all in terms of x. That's perfectly fine. And that's actually happening because in the original problem you couldn't disassociate the x and the y to solve for y alone very cleanly either. Now, this isn't actually a new concept, this number 9, something you've never done before. And the reason you haven't is because you needed to be able to talk about derivatives of logs before you could do it. So this is actually called logarithmic differentiation. And what that means is I'm actually going to use logs as I'm working with this to make it easier to take the derivative. Now, I suspect when you look at this problem, you're thinking, oh my word, I'm supposed to take a derivative. I see a chain rule, a couple of them. I see a product rule, I see a quotient rule, and this looks awful. And I would agree, it does. But what we're going to do is we're actually going to use properties of logs, which means we're going to take the natural log of both sides to start with. And so that may look like it's sort of making it worse, but I promise it isn't. So the reason it's not is because then on the right-hand side you can use properties of logs to separate or expand this form. And we did one similar to this, but much simpler earlier. So we're going to take each of these. So if I have the natural log of x squared, I could also go 2 ln x. Because I have multiplication next, I can do an addition sign. That square root is the same as the power of 1/2, so it becomes a coefficient of 1/2. And then again, I have an ln. I have the 3x minus 2. Okay. So I'm not taking any derivatives here. I'm just expanding with properties of logs. And then I have minus, because it's in the denominator. That exponent of 2 can also come out in front as a coefficient. And then I have the natural log of x plus 1. All right, so as I'm taking a look at this now, and only now, am I finally ready to take a derivative. So the natural log of y is 1 over y, and just like on the last problem, and then it's times dy dx. On the right-hand side, this will be 2 over x, because it's 2 times 1 over x. On this one we're going to have 1 over 2, because that's the 1/2. Then the 3x minus 2 is the rest of that denominator, and then we need to multiply by that inside function 3x minus 2's derivative, which would then be a 3. And then I have a subtraction of 2, and then I multiply by the derivative of this one, which is 1 over x plus 1. And the inside derivative here is a rather uninteresting 1, but we'll put it there just for the sake of saying we did it. All right, so we're not going to deal right now with that 1 over y until we get the right-hand side cleaned up, because the right-hand side is a mess in and of itself enough to worry about. And as we're looking at the right-hand side, basically we need to get common denominators. So let's take a look at what that would be. So I've got the 1 over y. Here's my dy dx. And I have this 2 that needs to be multiplied by both of the other denominators. So this will be times 2 times 3x minus 2. That's the first denominator after that fraction. And then I have it times x plus 1. My second denominator is a 1, and it gets multiplied by the x of the first fraction and the x plus 1 of the last fraction. And then I have a minus 2. I multiply it by the first denominator, which is an x, and then by the middle denominator, which is a 2 times 3x minus 2. And all of this is over x and 2, so I'm going to write that as 2x times 3x minus 2 times x plus 1. I promise it's going to clean up very, very nicely, at least nicer than it is now. All right, so let's take a look here. I mean, this really is just the number 4. So we actually are going to have a 4 we're dealing with here. And as we have this 4, we've got also a distributing, we can do a foiling on the inside here. So the 3x times x is 3x squared, and then I've got it times 4 out in front, so that's actually 12x squared. So I've got still the 1 over y dy dx, and now I've got 12x squared. Now the inside terms would be negative 2x and positive 3x. Well, negative 2 and positive 3 is 1x, and then I multiply that by the 4, so this is plus 4x. And then my last term is negative 2 times 1, so I have negative 2 times the 2 times 2 at the beginning of the 4, and that's negative 8. All right, so that's the first one. The other two are actually easier. This is just x times x plus 1, so it's becoming x squared plus x. Okay, and then the last one's actually 2x times 2, so that's 4x that we're going to distribute. So, well, negative 4x, sorry. Negative 4x times 3x would be negative 12x squared, which is actually really nice because I already had a 12x squared at the beginning. And then I've got the negative 4x times negative 2, which would be negative 8x. And again, all of this is over 2x times 3x minus 2 times x plus 1. All right, so let's combine some like terms. I have negative 12x squared and positive 12x squared, so that's rather friendly. Those two add to 0. I do still have an x squared left, however, in the middle, so I do have that. So I have 1x squared here. And then, I see here we have 4x and negative 8x, so that, and positive x here in the middle, so I've got negative 8 and positive 4, which would be negative 4, and another positive, which would be negative 3x in the middle. I feel like maybe I have left something out. So let's go back and make sure that I got those in there correctly. Just a moment. All right, there it is. I found it. We actually had a 3 missing back here. Right there is a 3 on that middle term that I totally left off, and it needs to be there, obviously. So instead of it being x squared plus x, it should actually be 3x squared plus 3x. So Let's make that alteration. So this should be 3x squared plus 3x. So I should have 3x squared in the middle here. And then instead of it being negative 3x here, I have a positive 4x. I have a positive 3x, so that should be 7x. And then I have actually I think it was supposed to be a positive 8x, so I made another error there, didn't I? Sure did. I got that sign messed up, so that's actually a positive 8 there. So I have a positive 8x, and a positive 4x, and a positive 3x, which makes it a positive 15x. And I think that fixed all my mess. And then, sorry about that, and then I have this negative 8 at the end. I have only one constant left on top. All of this is over 2x times 3x minus 2 times x plus 1. And, we haven't done anything with it yet, but now is the time that we would actually take care of the fact that that y needs to move so that I can solve for dy dx. So it's going to be moved by being multiplied on both sides. And we don't really need to multiply by y because we know what y equals. The y equals what we were originally given. So this is dy dx. The numerator of this actually does not factor, although you should check as you're looking at this to make sure that it doesn't. And in fact, what you're looking to just to really see is, does it factor in anything specifically that the denominator would match with, and it won't. So I've got the same fraction I had before, and I need to multiply that fraction by the original fraction that y was. So that was an x squared. It was square root. In fact, let me put it to the 1/2. So 3x minus 2 to the 1/2. And then it would be over x plus 1 squared. All right, so some things will simplify. The first thing that will simplify is this x. We'll mark out with one of these, so there's just one of those x's left. The next issue is that the 3x minus 2 and the 3x minus 2 to the 1/2 here will simplify. This one will go away, and this one will become a 1/2. In essence, you're saying you have two halves, or the number 1 of them on bottom, and you have 1/2 on top, so half of it cancels from each. And then the other thing that will simplify is that you can take this factor, and you can combine them to be cubed. So my grand result is 3x squared, cubed, because I need to distribute that power of x right here, or factor of x here. There's 3x cubed plus 15x squared minus 8. And this is all over 2 times 3x minus 2 to the 1/2, which you do not need to rationalize. You can write it as a square root instead of, if you'd prefer, but 1/2 is fine. And then also an plus 1 cubed in the denominator. So nobody ever said the logarithmic differentiation is simple. It is not. But the calculus involved is the easy part. Because of the way it works, the calculus that becomes involved is the clean and straightforward part of the problem. The messy part is the algebra at the end. So like I said, you're going to get really good at your algebra in Calc 2.